welcome to episode 2 of the Flag Tags. We're here today with Dr. Sherry Christian. We're going to talk about some immunology, we're going to look into some COVID-19 questions, a little bit about her research. So let's get started there.
There's actually 7 different types of coronavirus that infect humans. 4 of them only cause a very mild disease. So you feel like you have a cold. So, 4 are causing basically the common cold. The other one is MERS, which is causes Middle Eastern Respiratory Syndrome, and that originated in the Middle East. SARS, which causes severe acute respiratory syndrome. And then the SARS-CoV-2, which causes COVID-19. So MERS, SARS, and COVID are all very serious diseases. Interestingly, MERS and SARS did not spread like COVID because they were so much more lethal and they were much less transmissible. So fewer people got the disease, and the people who got the disease got very, very sick very, very quickly, so that disease was able to be contained very well. So SARS-CoV-2, which causes the COVID-19, is a lot milder in many, many people and a lot more transmissible. So the figure that people kind of tossing around now is for every one person who gets SARS-CoV, they'll infect 2 to 3 people. And of course, as we've seen when we have these big outbreaks, it ends up being so many people that get infected because of this exponential increase in transmission and infection. So, but like I said, it's more mild than these other severe coronavirus cases in that it's a flu-like symptom, but it's also very severe for some people. And I'll say that that's true for a lot of infectious diseases. So measles causes a mild disease in many people, but very severe disease in others. And flu, people still die from influenza virus. So it's the same idea, but in this case, there's nobody who's immune to COVID. So because so many millions of people everybody in the entire world is susceptible, it spreads so much faster, and we see all of these severe cases happening, it seems like all at once.
On that note, when you were talking about immunity for COVID, you hear people talk about certain provinces who've had a lot more cases and how they build like a herd immunity and how we're not really having that here. What's your opinion on that? How does that work?
So I'll tell you that actually there's no region in the world that has what we would call herd immunity. The idea behind herd immunity, though, is that enough people are immune that the virus can't spread. So if you're susceptible because you haven't gotten a disease, but everybody around you, all your family and friends are immune, then it's very unlikely that you can get the disease because they just can't spread it to you. So for that to happen, we need, upwards of 60-70% of the population to be immune. And when they've done recent studies looking at antibody responses, so one of the things that happens when you get sick with a virus is your immune system is going to mount a response, and they're going to make antibodies. And antibodies can block that virus from infecting. So we know that you've been infected if you have these antibodies. So when they look at people and ask, okay, in this population, how many people have been infected, they find that it's still less than 10%. So if in some cases it's like 1%, so this is not even close to what we're going to reach. News that one strategy to get through this pandemic is to let natural herd immunity happen. So just let the virus go through the population until enough people are immune. The problem with this strategy is that you're also going to get that fatality rate. So you're still going to get 4% of people dying because they've gotten SARS-CoV-2 and they've died from COVID. And for me, that's simply a non-starter. Like it's very unethical to think that would be a good way to achieve herd immunity. So the only way to achieve herd immunity is by a vaccine, because the vaccine is not going to kill anybody, but it's going to allow those people, so many people, 60, 70, 80% of people to become protected and become immune to that virus.
Compared to other viruses, it seems like the vaccine is taking a long time to develop. Do you have any opinions on that? Or
It's not. It's actually development of this vaccine is going at an unprecedented speed. So I think we feel like that because the flu vaccine, every year they make it new, right? But they don't really. They have all the knowledge to make a new flu vaccine every year. It's just a little tweak to change the protein that's in there, but everything else is known. So normally it takes 10 years to make a vaccine. So we have, maybe 2 to 5 years in basic research. So asking the question, what protein from that virus do we need to inject into a person to get a protective response, to get a protective immune response? Then we have to, the royal we have to test that vaccine to make sure that it's safe. So it's not going to cause any harm. Then we have to test it to make sure it's effective, so that it's actually going to be protective against that disease. Because if it's not effective, then it's obviously not going to work as a vaccine. Then we have to ramp up production of that vaccine and then actually give it to everybody who should be getting it. So all these vaccines that we have been in place for many, many, many years. I guess one of the latest ones, that you might you might remember being new would be the HPV vaccine. And that was, decades in the making. So the fact that we may have a vaccine next January, less than a year, is unbelievable, actually. And a lot of the research that was done on MERS and SARS is actually key to being able to have this vaccine so quickly, because it's already known which protein the virus uses to infect cells. And by targeting that protein, which is called a spike protein, so we can take the spike protein out of the virus and put it into the vaccine and get immunity against that spike protein, and it will be protective. So it feels like forever because we're so affected by this disease, but it's actually really fast.
A few questions people are asking. Like, I know a lot of people can't understand why there's no vaccine yet. And then I like how you talked about the herd immunity as well, because people are kind of talking about what's going on in the States right now. And they're wondering, are they going to be better off? And then this or that kind of stuff. So I felt like that was interesting to get an opinion on.
Yeah, the other thing the other thing that's really interesting about COVID is this, what they're calling long COVID. And so, when you recover from the flu or you recover from a cold, you pretty much recover. But it seems like for a large number of people, they actually suffer neurological symptoms or pain, or that's neurological, or lung symptoms or cardiovascular symptoms for a really long time. Well, there's only so long that they can be suffering, right? Because COVID's only really been around since the beginning of this year. But they're still suffering many months later from this syndrome. And it looks like it could be not even just one syndrome, it could be 4 syndromes. And I think that's going to be really interesting from an immunological perspective and a scientific perspective, but also a real challenge for everybody who's suffering. And I think this is one of the reasons that we can't go for herd immunity also, because not only are we going to get this fatality rate, but we are certainly also going to get all these people who are suffering for such a long time afterwards. And that is also not ethical.
Yeah, but no one really knows long-term effects yet, of course. We're not there.
Yeah, I was also wondering, can you get, after you have COVID, can you get reinfected from it after? Or is it?
So what we know from other coronaviruses is that people are immune, and so that immunity lasts for many, many months. Some of that protection may not be like lifetime protection. So in another coronavirus, you might get reinfected many years later because you've lost that immunity. there are some anecdotal reports, or maybe we'll say case studies, that where people have been reinfected and they've been able to show genomically that it's a new virus, but that is extraordinarily rare. And it probably is happening with other viruses as well. It's just that we're not capturing that information because we know that you get a cold pretty frequently. And so you would never like test that person to know whether it was exactly the same rhinovirus or coronavirus as they had before. So it's extraordinarily rare to get reinfected. Almost certainly, the vast majority of people will not get reinfected and will be able to have immunity.
Okay, that's good to know.
It's a problem, right? If you weren't getting immunity, the vaccine wouldn't work.
Yeah,
So,
it'd be really scary.
Yeah, it's a big question that seems like the answers are coming out as being yes, we are getting just a regular immune response that we get for every vaccine. SARS-CoV-2 isn't like this magic virus. It follows all the rules of immunology.
That's awesome. Okay.
All right. So let's talk a little bit about your research that you're doing at MUN right now. So what have been some of your most recent papers, or what kind of direction are you guys going in? What are your questions right now with your research?
So my lab is split into two main research directions. One is looking at the interaction between fat cells called adipocytes and breast cancer. So we know that being obese is a risk factor for breast cancer. So people who are obese get more severe cases and tend to survive less well. They tend to have larger tumors and a poor response to therapy. But we don't really know why that is. So some things are known, of course, like some of those interactions have been studied for quite a while, but it's not really known. All of the interactions are not known, and it's not really known how to interfere with that process. So what we've done is developed a model in the lab where we can culture breast cancer cells with adipocytes. And key to this is we also add something called extracellular matrix protein. So in the body and in organs, cells don't just exist in a fluid. They don't just kind of float around and bump into each other. They actually interact with each other. And many cells, including adipocytes, actually surround themselves with extracellular matrix proteins. And it forms kind of like a scaffold or a skeleton, a soft skeleton anyway, for the cells. And so we add extracellular matrix proteins to the co-culture of breast cancer cells and fat cells, and we actually see changes in the breast cancer cells that to us look like changes that would promote metastasis. So metastasis is when the cell kind of goes from the primary tumor and invades and colonizes secondary sites outside of that tumor. So that's what we think the adipocytes are doing, is actually promoting growth and attachment to secondary sites. So we don't know how they're doing that. So the next research questions are really to figure out and identify the molecules that are responsible for that particular change. That's one part of my lab. The other part of my lab is more immunology focused, and we're working on B cells. So B cells are those cells that make antibodies that are really important to be protective, and they develop in the bone marrow. So they start as stem cells, and they go through all sorts of stages to become a B cell that's ready to respond to some sort of foreign body and make antibodies. So the process inside the bone marrow is very well regulated. And there's a lot of proteins that will change their expression during those stages of development. We work on one called CD24. And what we found was CD24 causes the release of these crazy things called extracellular vesicles. So it causes cells to like bleb off little parts of them and release this into the environment. In other systems, we know that these extracellular vesicles can transfer genetic material or protein from one cell to the other. And in those recipient cells, it actually can change the way they function. We have no idea what these extracellular vesicles are doing in a B cell development context. So that's what we're trying to figure out. So we're looking at vesicles that go from one cell to the other and asking what are they doing in that recipient cell. Those are the things. Well, thanks for having me.
Yes, thank you so much for all the information. It was really insightful.
You're welcome.
All right.
So that's it for this episode, guys. Yep, I hope you guys enjoyed it.